Welcome to ShowOffer.io, where we're here to help you uplevel your interview performance and land your dream offer from top tech companies. My name is Tony, and I'm a technical coach on the ShowOffer platform. At ShowOffer, we specialize in helping candidates navigate the most critical parts of the interview process, from breaking down complex system design problems to prepping for behavioral questions, and even spotting red flags that could result in a rejection or lowball offer. We also offer insightful coaching sessions, live mock interviews, and personalized feedback, all aimed at making you a more confident, structured, and hireable engineer. Today, I'll walk you through one of the most frequently asked system design questions. Design Leaderboard. Leaderboards are widely used in products like gaming, social media, fitness, and education. Unlike ad-click aggregation systems that simply count events, leaderboards must maintain sorted rankings, support real-time updates, and handle time-based queries, e.g. daily or weekly top performers. They also differ from top K video systems, which typically rely on approximate counts, whereas leaderboards often require exact accuracy. If you watched our previous video, Design Top K System, you will find the similarities and great differences in design strategies with technical considerations. Let's start to explore for the next half hour. Let's begin by breaking down the requirements for a leaderboard system, one of the most common and practical system design questions, especially in gaming, fitness, and competitive ranking platforms. This is the backbone for features like real-time global scoreboards, region-based rankings, or daily challenges in popular online games. Functional requirements. 1. Submit or update player score. Players need to be able to submit a new score or update an existing one. Depending on the game logic, this could be the latest score only, the highest score ever, or a cumulative total, e.g. total XP. 2. Get top K players. The system must return the top K players based on scores. This is the classic leaderboard view, like top 100 players this week, or top 10 in North America. 3. Get players' current rank. A player should be able to query their exact rank at any moment. This could be based on global or filtered leaderboards and must reflect their most recent score submission. 4th, support scoped leaderboards. The leaderboard should be filterable by region, like country, continent, game mode, like solo, duo, arena, and time window, like daily, weekly, all time. Non-functional requirements. Similar to our previous Talk PI system, there is a key negotiation point, which exact or approximate accuracy. Technically, distribute heap is used for exact accuracy but recurring higher resource usage and complexity. Count min sketch is more resource efficient for approximate results. For designing a leaderboard which ranks players, we will focus more on exact accuracy in the following chapters. 1. Low latency. The system must provide a responsive experience. For leaderboard queries, such as top K lookups or rank retrieval, should complete in under 100 milliseconds. For score updates, it should reflect in the leaderboard view within 1 minute, ensuring timely feedback during gameplay. 2nd, high scalability. The architecture should support millions of score updates per second, particularly during peak events or global tournaments. Billions of total players or entries across game modes, regions, and time windows. 3rd, strong accuracy guarantees. Rankings must be exact and consistent, ensuring players see accurate positions and rankings across all views. Approximate methods may be considered for specific trade-offs, but exactness is the default expectation. 4. Cost efficiency. The system should be designed for resource efficiency at scale, minimizing compute, memory, and storage costs without sacrificing performance. Techniques like tiered storage, batch compaction, or selective materialization can be used to control operational overhead. With these requirements in place, our next step is to look at the high-level design, how score updates move through the system and result in real-time leaderboard changes. And this time, we will map each functional requirement to the data flow as well as building components and data schema needed. Let's move forward. To kick off the high-level design, let's start with functional requirement 1, submitting a user score. This is the most fundamental action in any leaderboard system. But even this seemingly simple step involves a number of nuanced design decisions, especially if we want the system to be scalable, accurate, and fair. Let's look at the core data flow. A user initiates the request from their device, the client, which sends the score to a score service. This service handles validation, transformation, and business logic. Once processed, the score is written to a score database, where we store records like user ID, score, rank, and additional metadata. The score service is stateless, meaning it can scale horizontally. But what it does inside is critical. It may need to validate the timestamp, check whether the new score is higher than what's already stored, update the leaderboard index, or emit events for downstream ranking updates. Here's an example of a REST API we might use. This API captures the essentials, a new score value and a timestamp. That timestamp becomes very important when dealing with time-based leaderboards, such as daily or weekly rankings. But submitting a score isn't just a write operation. It has several critical edge cases that must be handled gracefully in production systems, especially if you're operating at the scale of millions of players. Let's walk through 4 such cases. Edge case 1. The user submits a lower score. Should we allow it? In most systems, we only store the highest score per user. That's to prevent score regression or leaderboard manipulation. If a user submits a lower score, we might reject it or simply ignore it. Edge case 2. Duplicate submissions. Imagine a client retries the same request due to a network timeout. If we're not careful, we could double count the score. To prevent this, we design for idempotency, using a composite key like user ID plus leaderboard ID, or a UUID per submission. Edge case 3. Expired time window. What if someone tries to submit a score for a leaderboard that already ended? We need to validate the timestamp and either reject the submission or route it to a historical leaderboard to keep archival data clean and separated. Edge case 4. Ties in score. When 2 users submit the same score, we need a deterministic tie-breaking rule. For example, we might let the earlier timestamp win or fall back to comparing user IDs. This ensures rankings are consistent and predictable. These edge cases may sound minor, but they're what separate a staff-level design from a prototype. They ensure your system is fair to players, resilient under high load, and easy to maintain in the long run. So to recap, we ingest score submissions through a stateless score service. We validate the logic, timestamp, and update the database. And we carefully handle edge cases that affect leaderboard behavior at scale. Let's now explore functional requirement 2, querying the top K users from the leaderboard. In a high-scale leaderboard system, serving top K rankings in real time can become a serious performance bottleneck. To solve this, we rely on a proven technique, pre-computing leaderboard rankings ahead of time. This avoids live computation on every query, reduces load on primary stores, and gives us the ability to serve low-latency results, even during peak gameplay. Here's how the data flows. After a player submits a score, the score service writes to the score database as before. It also notifies the rank service, which coordinates rank updates across the system. Then, at regular intervals, a periodic or streaming job runs to compute the current rankings. This job calculates the top K users per leaderboard, as well as each user's rank. The computed result is stored in a table like this. This schema lets us retrieve rankings and top users with fast indexed lookups. It also enables historical leaderboard views, like daily, weekly, or monthly rankings, using the time window column. To generate this table, we can use tools like Apache Spark, Apache Flink, or Airflow. These jobs might run every 30 seconds, 1 minute, or 5 minutes, depending on how fresh the leaderboard needs to be. Now let's talk through the trade-offs and system-level considerations that come with pre-computing rankings. First, data staleness. Since we're computing ranks in batches, there's always some delay between the latest score update and the reflected leaderboard. We can mitigate this by tightening the batch interval or overlaying a real-time write-through cache for the most recent scores. Second, infrastructure complexity. Pre-computation isn't free. It requires stream processors or batch pipelines, metadata tracking, and monitoring. To reduce operational overhead, we can rely on managed data platforms and set up alerting for failures or delays. Third, storage overhead. Every leaderboard times time window times user tuple takes space. We need to apply TTL policies to expire outdated records, archive older data to cold storage, and roll up fine-grained snapshots over time. Fourth, late or out-of-order events. If score updates arrive after the relevant window has closed, we may miss them in the rankings. Stream engines like Flink allow us to set event time watermarks and run catch-up jobs to fix those gaps. And finally, computational cost at scale. When leaderboards are segmented by multiple dimensions, like region, game mode, platform, and time window, the number of required computations grows rapidly. We can prioritize high-traffic leaderboards and apply approximations for long-tail or experimental use cases. In summary, pre-computing leaderboard data is the foundation of fast, reliable top-K queries at scale. It reduces real-time load, improves user experience, and unlocks historical insights. But it comes with challenges that must be addressed carefully, especially at staff or EM levels. Let's move on to functional requirement 3, user rank lookup. In a leaderboard system, one of the most common and user-facing actions is simply this: where do I rank right now? Whether it's a gamer checking their standing in a tournament or a user comparing progress in a fitness app, this feature must be fast, scalable, and accurate. The way we implement it depends heavily on the system's performance goals, particularly how we balance latency, accuracy, and scalability. We'll explore 3 major strategies for supporting user rank lookup. Option 1. Real-time and accurate rank. If the goal is to deliver real-time and exact rankings, we can use a data structure like a Redis sorted set, also known as a ZS set. In this model, each leaderboard is stored in memory, with entries sorted by score. Redis provides 2 native commands for user rank lookup: zrevRank function to fetch a user's rank, where a higher score results in a lower rank; zscore function to fetch the current score of a specific user. This approach is fast and precise. Reads and writes typically complete in logarithmic time, making it ideal for interactive experiences like live leaderboards during competitions. However, it comes with trade-offs. Redis sorted sets are in-memory only, so storing millions of users across multiple leaderboards can consume significant memory. Scaling horizontally requires careful sharding, and durability is limited unless you configure Redis persistence with RDB or AOF. So, if you need sub-100 millisecond reads with exact rankings, and you're willing to pay the infrastructure cost, this is the gold standard. Option 2. Scalable reads with relaxed freshness. If your system serves millions of read requests but doesn't need rankings to be real-time down to the second, a more scalable approach is to pre-compute user ranks in the background. This could be done with a batch or streaming job that runs every minute or so. Once computed, the ranks are stored in a Redis hash or relational database, indexed for fast retrieval. The big advantage here is that lookups become constant-time operations, just a simple key-value fetch. This is perfect for high-volume leaderboard reads, especially in mobile or front-end heavy apps. It's also more cost-effective, since it avoids keeping everything in memory and shifts compute to batch infrastructure like Spark or Flink. The main trade-off? You're working with slightly stale data. Depending on your batch interval, rankings might lag behind reality by a few seconds or minutes. It also adds some complexity. You'll need versioned caches, TTL policies, and jobs to manage freshness. Still, for most casual leaderboard use cases, this option strikes a great balance. Option 3. Count min sketch for approximate rank. When dealing with very large-scale leaderboards, we're talking tens or hundreds of millions of users, you may not need precise rankings at all. Instead, we can use count min sketch, a probabilistic data structure that approximates frequency counts using very little memory. In this setup, we count how often each score appears. To estimate a user's rank, we simply sum the counts of all users with a higher score. This gives us a fast and scalable rank estimation using minimal resources. It also handles high write throughput with ease and scales horizontally without complex coordination. But there's a catch. The results are approximate. You can't get an exact rank, and you lose the ability to display full ordering. So this method isn't suitable for highly competitive or user-visible leaderboards, but it's excellent for telemetry, analytics, or long-tail use cases. In summary, if you need real-time precision, Redis sorted sets are ideal, but expensive. If you want scalable reads with near real-time accuracy, use a background job to pre-compute ranks and cache them. And if you're working at massive scale and can tolerate estimation, like our previous video design top K system, CountMin Sketch is an efficient and elegant solution. Choosing the right strategy depends on your product's tolerance for latency, consistency, and infrastructure cost. As a staff engineer or engineering leader, these are the decisions that shape system reliability, user trust, and long-term scalability. The final functional requirement is multi-leaderboard and time window support. A modern leaderboard system doesn't just support one global ranking. It needs to handle many leaderboards, based on region, game mode, category, or time window. This introduces a new layer of complexity, requiring a system that's both flexible and scalable, while maintaining fast read and write performance. Let's walk through how this works. When a user submits a score, it flows through the score service, which writes to the score database and notifies the rank service. The rank service is now responsible for updating multiple Redis sorted sets, each representing a different leaderboard slice. For example, leaderboard, global all-time. Leaderboard, stat, daily, 2025, June 29th. Leaderboard, EU, weekly, 2025, week 26. Each key reflects a specific region and time window, allowing us to isolate and manage rankings independently. This structure supports queries like Top 100 in the US this week, or Your all-time global rank. This pattern ensures logical separation between leaderboards and makes it easy to control time to live, TTL, and data expiration policies. For instance, daily or hourly leaderboards can be set to expire after a few weeks, keeping memory usage under control. To support this model, we follow a consistent key format. This structure makes leaderboard data easy to partition, monitor, and clean up. But we must be careful. Overly dynamic keys can lead to unbounded growth, especially in Redis or fast access stores. Normalize input, validate windows, and apply access controls to prevent misuse. There are a few key considerations when supporting time-windowed leaderboards. First, compaction. To save on storage and improve efficiency, we can aggregate daily data into weekly or monthly summaries. This reduces the number of keys and allows us to retain long-term trends at lower resolution. Second, TTL and cleanup. We use expiration policies or scheduled background jobs to evict outdated keys, avoiding memory bloat and stale data. Third, window validation. At write time, we must ensure that incoming score updates target a valid leaderboard. For example, if a client tries to update a leaderboard from last month, we should reject it or redirect the write to archival storage. To support flexible filtering, especially from dashboards or analytics tools, we introduce a metadata layer. This metadata table might look like this. This allows us to list active leaderboards in the UI, purge outdated ones, filter by dimensions like region or game mode, and support full auditing and discovery. With this metadata structure, both admin tooling and front-end display become much more powerful and user-friendly. To recap, We store and update scores across multiple Redis keys, segmented by region and time window. We validate incoming writes, enforce TTL policies, and optionally compact historical data. And we use metadata to make the system searchable, queryable, and maintainable at scale. With this, we've covered all 4 core functional requirements: submitting scores, querying top results, looking up user ranks, and managing multi-dimensional time-based leaderboards. In the upcoming deep dives, we'll explore how to scale this system to handle millions of users, optimize for cost and latency, and deal with real-world production challenges. Let's dive in. Here comes our deep dive. When building a system that supports top K queries, such as returning the most viewed videos, top-ranked players, or trending items, you need to make important decisions around accuracy, latency, and scalability. There are 3 widely used strategies for this. 1. Distributed heaps, which provide exact results but are resource-intensive. 2nd, skip lists, which maintain sorted order efficiently and scale well. 3rd, count min sketch, which provides fast and memory-efficient estimates. In this deep dive, we'll walk through how these approaches work, where they shine, and what trade-offs to expect. Strategy 1. Distributed heap approach. We start with the most straightforward design. Assume all data fits in memory on a single server. A hash table stores the scores, and a heap helps extract the top K entries. This gives us a time complexity of roughly O(n) log K, where n is the number of unique items and k is the number of top entries you want. However, this approach does not scale. As the number of incoming updates or the total number of items grows, a single server will quickly become a bottleneck. The first improvement is to add a load balancer in front of multiple identical servers. This increases throughput but still assumes each server can independently manage the entire dataset in memory. To scale further, we introduce partitioning, where each server is responsible for only a subset of the data. In this model, each partition maintains its own local top K list. Then, to get the final result, we merge the local top Ks across partitions using an n-way merge algorithm. This distributed design is much more scalable, but it introduces new challenges. Challenge 1. Data replication. We need to replicate each partition to multiple nodes for fault tolerance. For example, a replication factor of 3 means every data point is stored on 1 primary and 2 backup servers. The challenge here is keeping all copies in sync, especially during failures or updates. A best practice is to take regular snapshots of each partition's memory, allowing us to recover quickly after a failure. These snapshots can be reloaded and combined with recent stream data to bring the node back to its latest state. However, these snapshots can be large, sometimes several gigabytes, and keeping them consistent adds complexity. Challenge 2. Rebalancing. When we add or remove nodes, we need to redistribute data among partitions. This often requires metadata updates, reassigning shards, and carefully transferring data. If not done properly, we could run into network partitions, memory overflows, or data loss. To handle this well, we use consistent hashing. Each node owns a specific slice of the key space, and new nodes are added by splitting or reassigning those slices. In dynamic systems, tools like Zookeeper are used to track which shard owns which data. They also help notify the top K service of which shards to query. Challenge 3. Hot partitions. In some scenarios, such as a viral video or a major live event, certain keys receive far more traffic than others. These hot partitions can slow the system down. Load balancing mechanisms like dynamic sharding or auto-scaling are necessary to avoid bottlenecks and ensure even distribution of traffic. Now that we've explored how to scale a distributed heap-based design, let's shift to an alternative that's frequently used in modern systems: the skip list. Strategy 2. Skip list. A skip list is a probabilistic data structure that maintains a sorted sequence of elements with multiple layers of shortcuts. Here's how it works. At the base level, we have a full sorted list of all elements. Higher levels are sparser versions of this list, essentially express lanes that help us skip ahead when searching. Each element is randomly assigned to one or more levels, which helps keep the structure balanced without complex rebalancing rules. To search for an item, we begin at the highest level and move forward as far as possible. When we overshoot or reach the end, we drop down one level and continue. Eventually, we reach the correct element using far fewer steps than a full scan. This gives us fast performance. On average, logarithmic time for search, insert, and delete operations. Let's apply this in a distributed setting. Each shard is responsible for a range of keys, such as player scores or video IDs. Each shard maintains its own local skip list. Some skip list levels have pointers to nodes in other shards, which help speed up cross-partition queries. For example, the lowest level usually points to other nodes in the same shard. The middle levels may point to nodes in neighboring shards. The top level could include pointers that cross the entire system. This gives the system the ability to quickly find, insert, and rank elements across a large distributed dataset. Skip lists are excellent for systems that need sorted indexing, such as real-time trending content, dynamic range queries like top K across a score range, concurrent access since they're easier to manage in multi-threaded environments, and sharding as the structure naturally maps to distributed nodes. Unlike balanced trees, skip lists don't need rebalancing. Randomness keeps them efficient over time, and if needed, we can extend their height and pointer structure to accommodate growth. That said, randomness does bring some complexity. On rare occasions, too many or too few high-level nodes can skew performance. Managing forward pointers across levels is also error-prone. And because randomness drives structure, debugging and testing can be tricky. Still, skip lists provide an elegant and practical solution for top K queries at scale, especially in real-time leaderboard systems. Strategy 3. Count-min sketch approach. Now let's look at a more memory-efficient, but approximate solution, the count-min sketch. This data structure is designed for fast, probabilistic counting of events in high-throughput data streams. It works by maintaining a two-dimensional array of counters and using multiple independent hash functions. When a new item arrives, each hash function maps the item to a position in a different row, and the counter at that position is incremented. To estimate the frequency of an item, we take the minimum value of its hashed positions across all rows. This value is usually an overestimate, but within a bounded error margin. Count-min sketch is extremely space-efficient. It's used when we need high-speed, high-volume processing, such as logging systems, telemetry data, or approximate analytics. However, it is not suitable for leaderboards. It cannot maintain ordering, doesn't support rank-based access, and can't deliver the exact precision needed for top K results. Instead, count-min sketch is best used when we care about frequency trends and relative popularity, rather than exact positions or sorting. For a detailed explanation of count-min sketch, refer to the Designing Top K YouTube videos in ShowOffer.io. To wrap up, if you need exact top K results, distributed heaps and partitioned hash tables are a good starting point, but they require careful handling of replication, rebalancing, and partition hotspots. If you want sorted access with efficient updates and range queries, skip lists are often the best fit, especially for real-time systems that need to be updated and queried frequently. And if you're working with very large-scale data streams where memory is a constraint and rough estimates are acceptable, count-min sketch is the way to go. Leaderboards are often implemented using skip lists because they naturally support the core operations required by such systems. A leaderboard needs to maintain a sorted list of players by score, allow fast updates when scores change, and efficiently retrieve the top K entries or players within a given rank range. Skip lists excel at these tasks. They maintain elements in sorted order and support fast insertion, deletion, and rank-based access with average O log n time complexity. This makes them ideal for real-time applications like online games, fitness apps, or competitive platforms where leaderboards need to be updated and queried constantly. Now let's come to the second deep dive topic. How does this design scale to billions of rows per day? As our system grows, so does the volume of traffic. A competitive leaderboard system at global scale can ingest billions of score updates per day and must support millions of reads and writes per second at peak. To handle this scale effectively, we need to think across multiple dimensions: write throughput, storage efficiency, query performance, and horizontal scalability. Let's walk through how this design evolves to meet that demand. Write path scalability. Handling billions of rows means absorbing massive amounts of write traffic, often spiking into millions of writes per second. The first upgrade is to decouple submission from processing using a messaging system like Kafka or pub/sub. This ingestion layer absorbs bursts of updates, buffers them, and smooths traffic spikes downstream. Next, instead of updating Redis or the database on every individual score event, we batch score updates into micro-batches, for example, every 1 to 5 seconds. These mini-batches are processed by asynchronous worker nodes, which distribute the work horizontally. This gives us high throughput with much better CPU and network efficiency. Leaderboard sharding. As your system grows, even a single leaderboard, like Global All-Time, can become a bottleneck. The solution is to shard your leaderboards. For example, we can create keys like Leaderboard Global Shard 1 or Leaderboard US Daily 2025 June 9th or Leaderboard Game Mode EU Weekly 2025 Week 26. Each of these shards is backed by its own Redis instance or managed within a Redis cluster. We assign users or events to shards using consistent hashing or range-based partitioning, ensuring even distribution and predictable routing. Sharding increases write and read concurrency, while also isolating failure domains. It also lets us scale specific leaderboards independently, like allocating more resources to active tournaments. Efficient storage management. Storing billions of records every day adds up quickly, especially when tracking fine-grained windows like hourly or per-region scores. To manage storage cost effectively, we use a tiered approach. For active windows, like current hour or today's leaderboard, we use Redis sorted sets. As data ages, we compact old windows into aggregate buckets like weekly or monthly summaries. Then we offload historical data into cold storage such as BigQuery, Amazon S3, or ClickHouse. This balance keeps active data hot and queryable, while keeping costs low for long-term analytics or audits. Pre-aggregation and caching. One of the biggest challenges at scale is query performance, especially for top K queries and rank lookups. To make these efficient, we pre-compute and cache popular results every few seconds. This allows our system to answer rank queries instantly, even during peak load. For example, frequently accessed top K results are cached in Redis. Popular user ranks are cached in Redis hashes or fast access stores. Less frequent queries, like historical or custom views, are served from warm caches or cold databases. This model creates a tiered storage structure. Hot layer, in-memory Redis. Warm layer, pre-computed rank cache. Cold layer, analytical databases. Each layer is optimized for a different SLA, ensuring cost efficiency and speed where it matters. Time window isolation. Another way to scale cleanly is to isolate leaderboard keys by time window. For example, Leaderboard Game Daily, 2025 June 29th, and Leaderboard Game Weekly, 2025 Week 26. By separating data this way, We avoid cross-window interference and prevent score updates from clashing across contexts. We also apply time-to-live, TTL policies or background cleanup jobs to evict stale leaderboard data. This keeps Redis memory usage lean and avoids retention issues. For custom or rarely accessed windows, we use lazy materialization, generating leaderboard results only when needed. This avoids unnecessary pre-computation and storage overhead. Horizontal scaling and service decomposition. At this point, our architecture becomes a collection of independently scalable services. A score writer service handles score ingestion and buffering. A rank query service serves user rank lookups and top K queries. An aggregation service manages batch compaction, rollups, and historical snapshotting. Each service can be scaled independently, deployed separately, and monitored with its own metrics and auto-scaling rules. We also introduce a distributed task queue, such as Celery or Kubernetes-based workers, to manage job execution and batch coordination across services. Final thoughts on scaling. Scaling to billions of records per day isn't just a matter of throughput. It's about building a system that is resilient to failure, friendly to operational costs, and smart about separating hot data from cold, reads from writes, and real-time queries from archival ones. A few practical tips. 1. Have a clear data retention policy. For example, store daily leaderboards in Redis for 1 week, then move to S3. 2. Decouple access paths. Not all users need sub-second performance. 3rd, monitor write amplification and memory growth, especially if caching user rank and top K per dimension. 4th, design for backfill and reprocessing, in case a time window misses data, or you need to recompute ranks. With these building blocks in place, your system is ready to support real-time competition at internet scale, with confidence, clarity, and consistency. Now let's talk about something that often makes or breaks real-time systems: consistency. In a leaderboard system, consistency doesn't mean perfection. Instead, it means having a clear contract about what needs to be up to date, what can lag, and how we handle conflicting or delayed updates. Consistency isn't binary, it's a spectrum. And in this deep dive, we'll explore how to define the right level of consistency for your leaderboard system, without sacrificing performance or reliability. 1. Write consistency. The first place we need to be careful is the write path. Leaderboard updates are often user-generated and come from different devices, networks, or even time zones. So what happens when a user submits multiple scores in rapid succession? Here are some common scenarios. A user submits a lower score that arrives after a higher one, maybe due to mobile buffering or network lag. 2 devices send concurrent score updates for the same user at the same time. An event is delayed in the pipeline, maybe stuck in Kafka or queued on a flaky network. If we don't handle these cases properly, the leaderboard might show the wrong rank. Worse, a player might lose points unfairly, hurting trust and creating user friction. So how do we prevent that? First, we enforce monotonic updates. In other words, we only allow score updates that are higher than the last known value, unless your game logic allows for score resets or drops. Second, we use timestamps or sequence numbers to determine whether an incoming update is outdated. This lets us reject stale writes without guessing. And finally, we apply conflict resolution policies like last write wins, or more commonly for leaderboards, highest score wins. This ensures the most meaningful result is what shows up in the final ranking. These right-side safeguards are essential, especially in distributed or mobile-heavy environments. 2. Read consistency. Now let's switch to the read path. This is about what users see and how fresh that data actually is. There are 2 main models. 1. Strong consistency means every read reflects the most recent write. This guarantees correctness but is difficult and expensive in distributed systems. 2nd. Eventual consistency allows for slight staleness, but guarantees that all reads will eventually converge to the correct value. This is more common and usually acceptable for most leaderboard use cases. For real-time experiences, like a live scoreboard, we often combine strategies. Use write-through caching so the freshest data gets served immediately. Keep pre-computed ranks cached with a short time to live, maybe refreshing every 30 seconds. And include metadata in the API response, such as a timestamp that shows how fresh the data is. For example, rank as of June 29th, 2025 at 2:32 p.m. This gives the UI flexibility to indicate freshness to the user, so they know if they're looking at live results or a recent snapshot. Third, cross-shard or aggregation consistency. Things get more interesting when your leaderboard is sharded. Imagine a leaderboard that's split by region, category, or time window. A user's score might be updated in one shard, but not yet reflected in a global merged view. This creates a temporary inconsistency that can confuse users, especially when their rank appears out of sync. Here are a few strategies to manage that. First, you can delay reads until all relevant partitions report their updates. This introduces latency but ensures correctness. Second, you can define a bounded staleness window. For example, this leaderboard is consistent within the last 1 minute. This gives users predictable expectations while giving the system time to synchronize. Third, you can implement read repair. If a cache miss or inconsistency is detected, the system pulls fresh data from all shards, remerges the result, and returns a corrected version, often asynchronously. These techniques help manage the complexity of consistency across distributed partitions, ensuring the leaderboard remains usable, fair, and robust. To recap, consistency in leaderboard systems isn't about achieving perfection. It's about designing for clarity and confidence. For writes, we protect against race conditions using score validation, timestamps, and conflict resolution logic. For reads, we balance freshness and latency using cache layers, pre-computation, and smart metadata. And across shards, we design for bounded correctness, incremental repair, and predictable user experience. Done well, these techniques create a leaderboard that feels real-time, trustworthy, and scalable, even under extreme load. We started with a familiar challenge. Build a leaderboard system that can handle millions of players, real-time updates, and custom rankings, across dimensions like region, category, and time window. Along the way, we tackled the hard stuff. How to scale ingestion to billions of rows per day, how to maintain accurate rankings in the face of network delays and race conditions, and how to optimize top K queries with data structures like skip lists and distributed heaps. Through our deep dives, we explored the real engineering decisions that power large-scale systems, like sharding, pre-aggregation, lazy materialization, and conflict resolution on the right path. These aren't just interview answers. They're production patterns used by the best infra teams in the world. If you watched our previous video on designing a top K video ranking system, you'll notice the overlap in principles. Things like memory-aware counting, bounded consistency, and event time alignment. Together, these two case studies form a strong foundation for any back-end engineer working on ranking systems, recommendation engines, or real-time metrics. There's more to come, from hybrid consistency models to explainable leaderboard insights. But if this gave you new mental models or helped you think more clearly under interview pressure, we'd love to keep helping. At ShowOffer.io, we coaches just like you to nail high-stakes system design interviews, especially for roles at Databricks, Meta, OpenAI, and other top-tier companies. You'll get personalized feedback, mock sessions with real interviewers, and detailed breakdowns like the one you just saw. Check out ShowOffer.io for the full write-up, additional practice systems, and information on how to work with one of our coaches. Thanks for watching, and we'll see you in the next video.